but how much is it going to cost? How many lives are going to be lost when we have another big earthquake? It's going to be tens of billions of dollars and hundreds, if not thousands, of lives lost.
NASA's newest satellite maps just caught California's ground doing something it has never done before. The crust is twisting, sections are lifting, quiet zones are whispering in rhythm. This is not routine drift. It is coordinated motion across the state's most dangerous fault web. Instruments see the land inhale and exhale like a machine storing power. Are we watching a harmless pulse, or the first steps of a chain that unzips the San Andreas from desert to coast? If the ground has started talking, what is it trying to say now? Signs from space. From hundreds of miles up, California looks calm. The Central Valley runs like a green ribbon. The Sierra shines in clean lines of granite, and the coastline curves as if drawn with a patient hand. Inside that calm, radar from NASA's INSAR satellites reads the ground the way a physician reads a pulse. In early 2025, the pulse changed. The maps that usually show gentle sideways drift along the San Andreas system began to show something else. Bands of color tightened into crescents. Contours arched and twisted. Patches that had been flat for years rose by fractions of an inch and then rose again. Places that normally crept stayed still. Places that normally stayed still began to move. Analysts reached first for the common explanations. Heavy rain can weigh on the crust and push it down. Dry years can lift it again. Pumping aquifers can warp the land around them. The GRACE gravity mission checked those boxes one by one and crossed them out. The mass of water was not the driver. The signal came from something deeper and heavier. The surface was not rebounding from rain. The crust itself was changing shape. Caltech's dense arrays picked up strings of microquakes, not as a roar, but as a series of faint rhythmic taps along bends and step-overs where faults couple most tightly. The pattern ran from Parkfield through the Carrizo and down toward the Salton Sea. It did not look like a single patch slipping and then going quiet. It looked like a line clearing its throat, then doing it again a few hours later, and again a few days after that. Tilt meters on ridge crests caught the same rhythm seen from orbit. GPS stations 100 miles apart leaned by the same small angle once seasonal corrections were removed. Independent baselines agreed. The signal was coherent, not noise, not weather. A slow torque building in rock that matched the satellite maps. Engineers who live inside these datasets began to talk about texture rather than trend. The crust had gained a new texture. It puckered and smoothed in cycles. The radar fringes wrapped like rings around islands of uplift that had not appeared in a generation. Between the Mojave's hardpan and the farms of Coachella, something in the lid of the earth was swelling as if pushed from below. The word breathing returned to briefing rooms. The fault looked as if it had lungs. No one at the Jet Propulsion Laboratory said the phrase on the first day or the second, because precision matters. By the third week, as the swaths stacked and the fringes tightened, more than one voice used the same sentence. The ground is twisting. When the ground twists along a boundary that holds two continents apart, the honest next step is not a claim, but a question. If the surface is practicing a new rhythm, what is pushing from below to set the timing? Pressure underfoot. To follow that push, research teams blended sharp images of the surface with blurry pictures of the deep. Seismic tomography outlined zones where waves slow down, which often means the rock is warmer and softer. Heat flow maps added gradients. Borehole thermometers supplied actual numbers from the dark. Gravity anomalies hinted at density changes that you cannot see, but can weigh. When the layers were laid together, they showed a lens beneath the Mojave and the southern Central Valley that had grown more buoyant and more mobile than earlier models allowed. It was not a bulb of ready magma. It was hot, ductile rock that can soften the base of the crust and bend the brittle layer above it. Imagine a thick glass tabletop resting on a pad of warm tar. If the tar bulges, the glass arches. The San Andreas runs through that glass. The arching does not break the surface, it loads it. GPS monuments driven into the Carrizo began to tick upward by a hair's breadth. INSAR painted those upward ticks in clean rings that repeated month after month. helium-3, and carbon dioxide rose a little in springs that cross the fault, a sign that deep rocks are being squeezed. None of these signals would matter alone. Together, they describe a system that is storing energy, the most stubborn puzzle centered on a reach that has not snapped end to end in more than a century. Locked segments earn that name. They resist motion while the plates keep trying to pass. Resistance builds strain the way a bent ruler stores tension. You cannot see the tension until the ruler straightens. In one internal summary, a geodesist wrote the sentence that others began to repeat. The fault is not slipping, it is loading. Slipping lets energy out, loading keeps it in. Modelers then asked a hard question and answered it with a boundary rather than a prediction. If the ductile lens continues to rise and the brittle lid continues to bend, where could the first break run and how could it spread? The answer was not a date and not a magnitude. It was a set of plausible paths. One path begins near the Salton Sea, races northwest at highway speed, and recruits strands at step-overs that past ruptures have left weak. Another path begins farther north, leaps south across a locked hinge, and drags the southern section with it. Either path is a chain rather than a single link. Neither is guaranteed. Both become more likely when the arch grows sharper. When a system stores energy in silence, the silence is not peace. It is a long inhale. Every millimeter of uplift is a small measure of air in the lungs of the state. Every spike in deep temperature is a small measure of warmth pressed closer to the lid. If the inhale continues, to what note will the exhale fall? When the quiet starts to speak. The stillness along the San Andreas carries its own voice for those who know where to listen. In late 2024, that voice changed from a murmur to a pattern. Broadband seismometers buried under hayfields near Parkfield and beneath the dry shoulders of the Santa Rosa Mountains began to record tremor bands that drifted like a faint tide along the fault. The bands lasted for 10 minutes, then 20, then half an hour. Hours later, another band would appear a few kilometers away. The timing did not match human schedules. It matched nothing but the fault's own map. These low-frequency tremors are not like the sharp snaps that knock pictures off walls. They are slow slips that take place 15 to 25 kilometers down, where rock is warm enough to flow a little and cold enough to hold. Fluids at depth find micro cracks and press inside them. Pressure reduces friction. The rock slides a millimeter or two. The pressure bleeds. The crack closes. The cycle repeats. None of that is dangerous by itself. What matters is where these cycles run and how they migrate. They tend to choose the tightest joints in the network, where a small nudge in one block is felt by the next. The tremor trains in California tracked the most coupled reaches of the San Andreas with unnerving care. They lined up with places where other faults touched the master fault. They gathered around bends where past ruptures had paused and then jumped. They accelerated, not by a lot, but enough to show a curve rather than a flat. Their cadence echoed the months before major events in distant places whose physics is not identical, but whose rules rhyme. The crust rarely writes the same sentence twice. It often uses the same verbs. At the surface, roads did not ripple, dogs did not bark, lamps stayed quiet. In the ground, the conversation grew louder. A set of instruments beneath the Coachella Valley recorded faint electromagnetic pulses at night, a signal that quartz-rich rocks can produce under stress. Thermal cameras that mapped the desert floor in the same hours traced narrow, warm lines that matched shallow traces of mapped faults. The lines did not blaze, they breathed. The pattern that worried the people who read it sat at the edge of language. It looked like a zipper opening 3 teeth and closing 2, then opening 4 teeth and closing 1. If that is practice, who sets the tempo and who plans to lead when the tempo quickens? Maps that refuse to stay still. Numbers ask to be believed when independent methods converge. In late 2025, a joint synthesis combined Sentinel and NISAR interferometry, continuous GPS, grace gravity, borehole temperatures, and updated seismic velocity models from Caltech and USGS. The public summary used spare phrases. Uplift is broadening. Eastward tilting has appeared on range fronts, once treated as neutral. Gravity changes are consistent with density reductions at depth. The private discussion was simpler. The crust is twisting. You can picture it without math. Hold a towel by both ends and twist gently. The fabric does not just stretch, it rotates as it stretches. California is not a towel, but the analogy holds at the scale of a few millimeters across hundreds of kilometers. The twist concentrates stress along particular lines and relaxes it along others. Survey crews who live on the ground saw the same message in small signs. Steel benchmarks that had matched their coordinates for 2 decades drifted by a few millimeters. Fence lines that cut across rural traces of the fault grew gentle doglegs that experienced workers noticed even when satellite images could not. In the Coachella Valley, repeat pass radar outlined ripples in the desert floor that were not there 5 years ago. Irrigation channels near Hollister showed micro-tilts that engineers had to correct with shims. A handful of wells rose and fell in step across counties that do not share aquifers. None of this proves a date. All of it marks a change in posture. The system is no longer idle, even while it looks calm. Inside conference rooms, scientists faced an old dilemma with better tools. How do you describe a pattern that has preceded large events elsewhere without promising that it will precede one here? They reached for the careful language that keeps trust. Heightened activity, anomalous uplift, accelerating strain. The phrase no one wrote on the public slide sat on the whiteboard when the door closed. We are watching a system move from elastic behavior to inelastic behavior. Elastic motion springs back. Inelastic motion does not. A second synthesis focused on the fault web rather than the master line. The garlock crept by a few millimeters where it has not crept in the modern record. The San Jacinto's deep noise rose. The Hayward whispered for the first time in years. The timing lined up within days. The mechanism does not require mystery. Stress moves. It hunts for the path of least resistance. When a locked segment holds, strain finds another door. When several doors give at once, the house breathes with one chest, a web that pulls tight. The San Andreas is a backbone connected to ribs. The ribs matter. When the backbone flexes, the ribs do not get to ignore the motion. In 2025 and early 2026, the ribs began to flex in sympathy. Small shifts along the garlock appeared in a place that had shown none since instruments were set there. Deep noise grew on the San Jacinto. The Hayward, which cuts through a dense corridor in the Bay Area, recorded a thin band of tremor that came and went with a rhythm no one had catalogued before. The message was not volume, it was timing. These changes did not arrive months apart. They stacked within days. Computer experiments that let faults trade stress in virtual rock reproduced the same choreography when the main fault was pushed toward higher load. The physics is plain and hard. A locked section gathers strain. The plates do not stop trying to move. The strain has to go somewhere. It travels along the web and waits for a weakness. When several weaknesses reach the same threshold, motion can involve more than one strand. History offers examples. The 1906 rupture changed stress far to the south. The 2019 Ridgecrest sequence woke faults 20 kilometers away. Those were narrow lessons. The present web is wider and more awake. Signals outside the usual playbook added weight. Nighttime magnetometers logged repeating pulses that rocks under pressure can produce when quartz grains distort. Thermal imagers found thin lines of warmth that traced shallow strands, heat from microscopic slips that release friction in increments too small to feel. Gas samplers on the desert floor measured small upticks in carbon dioxide and radon where fractures pass fluids upward. Hydrologists who know the smell of a well after rain said these wells smelled like stone being squeezed. None of these details tell a fortune. They draw a frame. The frame holds a picture of coupling. Segments that had acted like neighbors began to behave like kin. In a family, a nudge does not stop at the shoulder it touches. It travels through muscle and bone. A system that has pulled tight is not guaranteed to fail in one dramatic motion. It is guaranteed to carry disturbances farther than before. If the web has tightened, what counts as a small event now? How many small events add up to a step the whole body feels? The breath before the note. California wears calm like a well-tailored coat. Sunlight softens the valleys. Freeways hum without a tremor. Coastal towns sleep under marine layer and wake with coffee over quiet water. Beneath that coat, two plates lean and push in a way that invites sober metaphors and rejects melodrama. Seismologists call this interval the interseismic phase. It is not a warning siren, it is a long inhale that can last a lifetime. The inhale is not danger by itself. The danger is how it ends. Stress models now put the southern San Andreas at levels comparable to the early 19th century. Simulations show how a rupture that begins near the Salton Sea could sprint northwest, take advantage of weak spots left by old breaks, and deliver shaking to the Los Angeles basin for more than a minute. A minute is not a number on paper. It is a span in which untuned structures tire. It is a test for lifelines that cross the fault, pipes that carry water and gas, lines that carry power and data, arteries that keep a modern state alive. A detail in the latest satellite runs stands out to the people who stare at pixels for a living. When the southern reach lifts by a small amount, the northern reach sinks by a matching fraction, and then the sign reverses months later. The pattern looks like breath moving through a chest. Field crews found hairline cracks in rural roads that opened by a finger's width overnight and narrowed a day later. Wells a county apart rose and fell in step despite drawing from different aquifers. The ground is not moving in one place while the rest watches. It is moving in a coordinated way that instruments did not catch a generation ago because the instruments were not yet this good. There is no single line to cross, no red light on a control panel that trips from safe to unsafe. There is a posture that a loaded system adopts when it approaches the moment it chooses to change. The posture is visible now to satellites, to GPS pins, to small thermometers in deep holes, to seismometers that listen at frequencies too low for bones to hear. The posture does not fix a date. It does not promise a magnitude. It says that a machine built by nature to store energy in decades and release it in minutes is closer to release than it was. That knowledge carries an edge that is more human than technical. If a landscape can show its rhythm before the first note, do we learn to move with it, or do we wait to name the note after it arrives? The fault will keep its time. The only choice is whether people choose to keep theirs. The ground is practicing. The breath is audible in the data. The downbeat has not sounded. When it does, the story will not begin. It will continue a measure we have been hearing for years, in signals that were quiet until new eyes learned to see them. From orbit, the fault looks like a thin line. On the ground, it is a boundary between ordinary days and the minutes that rewrite maps. The new images and the low hum of tremor do not predict a clock time. They tell a simpler truth. The system is awake, and it is sharing its pressure across a web that reaches from desert to coast. California has lived with that truth before. What is different now is how clearly we can watch the rehearsal. We can see the land inhale and exhale. We can hear the slow notes moving under our feet. The silence between those notes is not empty. It is the sound of a machine storing its next measure. When the ground chooses its downbeat, the story will not announce itself with certainty. It will arrive the way all deep events do. First as a shiver in the data, then as motion in the street. Until then, one question remains. If the Earth is already speaking, how closely are we willing to listen?